And that is easily the worst thing I've ever done in my entire life. See, probably not you guys because you're all here right now. Okay, in 4.6, our last section in chapter 4, our focus is going to be on the idea of congruence in overlapping triangles. So very specific situation, but there's places where this makes sense to do. Now, I've never been to New York City, but I've heard that New York City is really easy to get around because of the way that they have their streets set up. Salt Lake City is the easiest city I've ever seen to navigate because when they built Salt Lake City, it's perfect squares everywhere, and the numbering, like, they thought it out better than any other city. So it's very clear where you're from, because if you were to look at a map of the streets of Salt Lake, for example, here's the temple, and that's my temple, just so you know. It's a Mormon temple, but there's a south of the temple, there's a north of the temple, there's a east of the temple, and there's a west of the temple, right? So if you want to just name all your streets in reference to this, which in Mormonism, the temple is a big deal, so Salt Lake City is a lot of Mormon people, makes sense that they use this. But you just say, here's 100 east, here's 200 east, and they just go through 1 east, 2 east, and they just start counting up. And you can do the same with north, south. You don't even have to worry about streets or anything. You just have to tell me what are the numbers east and west, and you know exactly where it is in relation to this. And it's so easy to get around. If you looked at a map of the streets of our lovely community that we don't have a temple or any central feature to really base stuff off of, are our streets nice and perfect like this? I don't think so. And if you're not really sure, I challenge you, any of you, to give me your address, and I will have no idea where it is because nobody knows streets here because none of them make sense. They don't go the same way like they do in a regular city. Okay, now I'm not really, like, it might sound like I'm complaining. I'm not. Like, we live in a unique geography. It's a weird shaped island that's just slowly developed over time. Anybody ever been to the East Coast before? Boston? Have you been to Boston? You've never driven in Boston. How old were you when you went, though?
This was 3 years ago.
Did you notice the roads were any better or worse than anywhere else in the world?
Yes.
Better or worse?
They seemed not as rough.
Okay, so the stuff itself makes sense. Boston is one of the older cities in our country, right? If you didn't know that, it's on the East Coast, and because they started really small initially, if I said, think about a city block. Now, here, we don't really have blocks necessarily, but in bigger cities everywhere else around our country, I suppose the Philippines as well, there's blocks, I think. Is that true in the Philippines? Okay, when I say imagine a block in your head, what shape are you thinking? Like, even with a street, like a city block, you're thinking a square, right? Here's Boston, and let's see if we can't zoom in on this. Nope, not buying at Amazon. Get out of here. Not today. Oh, Black Friday's coming, though. All right, we're just going to go to maps. Why wouldn't I do that in the first place? This guy. All right, so here's Boston, or Boston, if you will. And look at this. Look at all these perfectly nice and square streets that make so much sense because, of course, at Hawley in Washington, you get a block that now has 5 sides. Or this one that looks like Oklahoma with the panhandle right here. Like, it's wonky, and our streets here are pretty wonky too, and it makes sense. We don't have these blocks. Now, in a lot of cities, they do. So one of the things that we're going to look at, and an easy way to apply this, is if you're going to be a cartographer, which I don't think there's a whole lot of employment opportunities for cartographers anymore. What does a cartographer do? They make maps. Now, obviously, we still need to make maps today, right? But it's through software. It's GIS is what it's called. Don't know what the symbols are for, something with satellites, but it's satellite imaging, and use that to help make maps. However, we're going to look at the following problem. And for these, just like the other one, and this is so crazy because check this out. I lied. We'll get into it. Okay, let's just start hopping in. I want us to get more practice with some of our congruent stuff, and then we'll get to the streets. Sorry, I was so excited to do the map stuff. Not a huge map nerd, but it's cool when it applies. Here's what we're going to do. I want us to find, and this is just CPCTC, is what I'm going to label our first little topic. And what does it stand for? That's right. Corresponding parts of congruent triangles are congruent. Okay, that's it. Now, sometimes this is pretty straightforward to use, especially if they're separated, but it can become more of a challenge if we start to mesh stuff together. And that's natural. We're just going to see if we can't identify. And I'm going to use the shorthand ID for identify corresponding parts of the following figures. And we're just going to see, before we do anything, we're just going to try to see if we can identify them, and that'll help me decide how fast we can go through it. Okay, now that's it. Identify some corresponding parts. So here we go. Now, I should say if possible, because they'll always be corresponding, so I'm good with that. So let's take a look-see. I'm going to draw this lovely, I don't know what to call this shape. I'm going to draw, oh my gosh, my stuff is lagging and I don't know why. But I'm going to draw this lovely triangles. So we'll do it that far. Then I'll come up here. We'll do it like that. We'll do this. Okay. Now, I have a bunch of triangles up here, and there's many of them. How many triangles do you guys count on this figure?
At least three.
At least 3. I agree with you. I think there's 5. I think there's small, 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 and I'm just going to cover it up, big, and big. Okay, I think there's 5 here. Now, we're going to add some labels to this bad boy, so I'm going to pause it so we can get out of the editing stuff. What rule would you use here? So careful. Do we know the triangles are congruent yet? So I like that idea. Like, I want to use that also, but until we know that these triangles are congruent, we can't use the fact that they're congruent to find corresponding parts. But are there angles in this circle that you guarantee are the same? And I'm going to zoom in because this is way too small, so I can add some better label stuff. Why do I think this is true? And I'm going to use dashes so I can sort them out. Because they're vertical angles. Everybody agree with that? Okay. Now, right now, depending on which triangles, and I'm going to have to draw and undraw a bunch of times because we need to be able to trace and make sure we're talking about the same stuff. Anything else you can guarantee is the same? ZX and what?
ZX and BX.
Why?
Because they share the same side. Well, not like. You know what? Never mind.
I think you're onto something, but I don't necessarily love your logic. It is there. I do agree that these are the same, but I need to know why. Ray, what do you think? VZ is congruent to itself, right? I can use that. Let's mark it. Might as well. This is congruent to itself. Okay. Now, if you'd like, and totally optional, you can write it if you want, but if anybody wants it, I would just say this one is just vertical, right? Just to make sure we get practice with this. And why do we mark that one? It's not congruent to anything other than itself. How do we know that's true then? Why is it congruent to itself? What's the name of that? Good. So there's the reflexive. And this will look less blurry when I zoom back out. Okay, anything else? I want to really focus on what Lily was saying, but we're going to find the right justification for it. Lily thinks correctly that that and that are the same. Why? Now, I'm going to point you in the way that I think about it. If I look at just that triangle that I had, and I guess I could put it back, I think it's an isosceles triangle. Lily also thinks it. Why? So the base angles. Now, this drawing here that they've done, and we have to be careful with how this makes sense, because when I look at this, and this exact picture they have in the book, I think of this as being angle V as a whole and angle Z as a whole. But if we think of it the other way, it works all the same. Do you agree that just this angle, which we could say is ZVX right here, is just one arc minus double arc? Do I get one arc minus double arc right here also? So then I know that this angle, just the inside part, and this angle are the same. And if they're the same right here, they're the base angles of an isosceles triangle, and it would mean that these are also the same. Okay, so we had to kind of go roundabout. I'm going to mark them, though, now that we've hit that. Do you guys, were you able to follow the logic that I just had? So from this one, the orange marks that we just added, and we'll just make it to both of them. This was simply the isosceles theorem. And we don't really have to justify, it's just good practice, because that's oftentimes where people struggle with proof. The isosceles theorem, and we used just a smidge or a small amount of angle addition just now. Okay. Now, with just those marks, I think we're pretty close to being able to give a lot of congruent stuff. And these problems, it can be hard to do this. There's a reason we're not like doing all of them. I think right now I can confidently say that there are a couple of triangles that are congruent. Which triangles can you guarantee right now with just the marks that we have are congruent to each other? WXV, so I'm going to write it over here, and I'm lagging so hard, driving me crazy. Triangle WXV. I'm just going to look, I'm going to draw WXV. And notice what I do. I go blank. It's a small triangle, so it's probably going to be the small triangle over here. Reasonable. But it goes blank to weird arc to double arc. How do we go blank to weird arc to double arc on the other one? YXV. Z, I'm sorry. Okay, Y to X to Z. Everybody agree with those? Now, all of a sudden, we get to use these corresponding parts, because now that we have two triangles that are congruent, then we can say that all the corresponding parts must also be. I want us to look very closely. WV on this congruent statement is the first and third term. What's the first and third here? So I know that WV and YZ also match up. I'm going to use my weird dash now. We'll do that one. And how do I know that's true? It'll link with this. Corresponding parts of congruent triangles are congruent. Okay, so we're working our way through. Like, it's strange because I didn't really ask you to do anything other than tell me what's all the same. And we have to get to congruence to be able to do that. Now, by putting these marks, I'm going to shift my focus away from small triangles. Do we have big triangles here too? And very specifically, I'm going to use purple. Actually, I'm going to use bright. I don't know what color to use. Red doesn't work, but we can try to make it kind of pink-like. Or a different shade. I don't know. What color do I want to use? Pink? Can you guys see this? Okay. It looks almost the same as the other one. Anywho, let's look at this triangle. Boom, boom, boom. Now, I'm just going to write it because we've already committed to it. If we write that triangle, the order doesn't matter. I'm going to call it VWZ. Is there another triangle up here that is the same as VWZ? And it can be kind of hard, but if we're looking, I'm just going to make the marks purple so it's easier to keep track of. Like, the pictures get really convoluted, really full of stuff. And they should. There's a bunch of stuff that overlaps. But on VWZ, this is V, right? And there's Z. Just kidding. This is big angle Z, but we'll get there. But I want to look at that triangle and then this triangle here that we'll do in this color. These two big triangles. Do they already have a common angle in V and Z down at the bottom? Are these sides on both triangles and have the same mark? So we go from a side to an angle. Can we get the next side? Side, angle. Is that side congruent on both triangles? So we just used what? SAS. So if we follow through V to W to Z, and we're looking at the big triangle, it's 1 to none, and then third angle. So 1 and I guess, or angle, cross dash, and then angle, cross dash, third point. Are you okay with that? Angle, we start at what? What matches up with V? Z, and my pink color is going to change because I didn't save it. This is congruent to triangle Z, and then if we cross dash, what's the next point we hit? Y, and we end where? V. We have a ton of congruent stuff everywhere. What I'm not going to make you do, because we already did it with all of our pictures, if you look at the example similar to this in the book, their answers are so much more involved. They say VW is congruent to YZ, and that angle WXY, we could list them all out. I am completely okay as long as we're marking our pictures. I'm not going to physically make you write them all if you're cool with that. Like, that's going to save you like 10 minutes on each problem. Do that. Mark the pictures. It means you have to draw the pictures big enough to mark them. I would encourage you, this is good stuff just to practice with, making sure that we get these justifications. We're not really proving anything, but we could prove all this. Okay, should we do another one like this, or feeling okay so far? Okay, we're going to meet in the middle then, since we only got one feedback. We're going to do another similar problem. We're going to shift focus just a little bit. So the good news is that you guys get to copy a photo. And here's our photo. And I want you and I and all of us together are going to do this proof. Cool. I'll give you a moment.